Welcome to Nole Edge, the official podcast of the College of Arts and Sciences at Florida State University. I'm your host, Amy Walden, the Assistant Director for Visual and Social Media with the College of Arts and Sciences. And today we welcome Aaron Wilber and Emily Salvador. Aaron is an Associate Professor of Psychology and Neuroscience here at FSU and leads the Wilber Lab on campus. And Emily is a graduate student in the lab. Aaron and Emily, thank you so much for joining us today.
Thanks for having us.
Yeah, thanks for having us.
So on today's episode, we're exploring some of the neuroscience behind Alzheimer's disease, a progressive disorder that affects memory and behavior in millions of Americans, which currently there is no cure for. Today, we're discussing what researchers are learning about the disease from studying what occurs in the brain on a molecular level, especially during sleep. So before we dive into that, Aaron, we'll start with you. How did you first become interested in studying psychology and neuroscience?
I started in undergraduate working in a lab doing research on alcohol. Not a topic I was terribly interested in, but just getting my feet wet. And I decided that I could probably help people better if I went into a field where I directly work with people. So I was an occupational therapist, long story short. After some time in St. Louis, doing some training, I worked in Chicago for about a year and realized this was not for me. And part of the reason I realized it wasn't for me was that what I felt like a lot of the practice, especially the parts related to learning and memory, which is kind of one of my longstanding interests, were not based on a lot of research. They were often based on, guessing or practical knowledge or those kind of things. And so I realized there was a big hole to fill, and I could probably do a better job of helping people if I filled some of those gaps in our knowledge. And so I went and spent about 4 more years in St. Louis working in a lab at WashU, making sure before I changed careers. So I didn't do that too many times or run out of lifespan, and quickly decided it was the right thing for me and went to grad school and ended up here.
Excellent. And Emily, how did you first become interested in neuroscience and learn about the Wilber Lab?
I actually went here for undergrad at FSU, and I was in the cell molecular neuroscience program. And one of the classes was research methods. And in research methods, my TA told us that we could get class credit by volunteering or being a student in a lab. So I started reaching out to professors. I started telling them, hey, this is my name. These are my interests. I have no research experience, but I'd love to get some. And Aaron actually came to one of my classes in my junior year, also a research methods class for neuroscience. And that's where I first learned about the Wilber Lab. And funny enough, 2 years later, I ended up being his student.
Excellent. So what areas of research are you focused on at the Wilber Lab, Aaron?
Our lab has kind of 2 overarching main areas. One of those is how your brain allows you to figure out where you are in space, so a larger across campus kind of space across a big city. A few parts of how you do that are of interest to us. One is learning a memory, including the formation of learning a memory while you sleep. Another big area for us in that area is looking at how you interact with the world in very much a body-centered or body-fixed way. So you see things in front of you or to your right, and yet for whatever reason, I don't know if we fully understand why this is, your brain, at least parts of your brain, tend to map out space, even if you're not the kind of person that thinks this way, probably, and very much map-like or world-centered space, so kind of like your GPS map space. So that means you have to interface between these 2 ways of interacting with the world, this body-centered or person-centered, and this map-like. So we're very interested in how your brain allows you to get in between those 2 things. And then the other half of what we do is the one we're here for today, looking at what goes wrong with those same brain systems and abilities in the context of Alzheimer's disease. And then there's 2 main areas there. I think we're going to talk about both of them a little bit. One of those is looking at brain activity patterns during sleep and how that may be dysfunctional in Alzheimer's disease and more importantly, may contribute to inability to form strong memories. Some Alzheimer's disease is kind of known as being a memory disorder. And the other part is looking at sleep in a little different way as a way to clear out or remove some of the pathology that tends to build up and eventually cause some of the problems in your brain and in your behavior later down the road that are manifest in the symptoms of Alzheimer's disease.
And yes, I'd love to talk about your work on Alzheimer's disease. So it's a brain disease that causes a slow decline in memory, thinking, and reasoning skills. And early symptoms can include difficulty remembering recent events, confusion, misplacing items. Aaron, in 2021, you were awarded a 5-year, $2.2 million grant from the National Institutes of Health's National Institute on Aging to study sleep-related brain function in Alzheimer's disease. Can you tell us more about how this project first got started and what you were hoping to find?
Yeah, so I actually started this work back when I was a postdoc in California at UC Irvine, when I got interested in expanding into Alzheimer's disease. At that point, I hadn't done Alzheimer's research. And so I developed this idea there that has continued all the way up through this R01 that we got here. And that's actually getting towards the end of the grant. We're writing a renewal right now to try to get more time to look at a different angle of that idea. But the idea going into that grant, to answer your question, was that, again, people hadn't really looked for evidence of something that seemed obvious to me at the time, that one of the ways you can get memory disorders is to have a hard time forming memories, which is where a lot of the research up to then had focused. But another way is that part of your memory formation process, we think, is that your activity patterns in your brain that happen while you're sleeping. We don't think all of those are for building memories, but there's pretty good evidence that seems to translate well into humans, that some of those activity patterns are designed to strengthen or build or form a memory of what even just happened that day. And so we wanted to look and see if those activity patterns during sleep were disrupted. Test the hypothesis, if you will, that disruption of those activity patterns might predict some of the cognitive impairments, if you will, in Alzheimer's disease.
Emily, did you want to add anything?
I guess from a simpler point of view, I think one of the biggest challenges to overcome is accessibility, and not just accessibility to knowledge itself of what's going on with, Alzheimer's research, but also accessibility of understanding what's going on in the system. There's a lot of things that we can't perfectly replicate in humans just because the materials themselves aren't accessible. Studying the proteins, as the pathology Aaron keeps mentioning, some molecules that are building up in the brain is very difficult to do imaging-wise, or there are some very painful and invasive procedures like spinal taps where they can look at that, but people often don't want to volunteer, and especially if someone is experiencing intense cognitive decline, they're not in their right mind to give consent. So I think accessibility is one of the biggest things.
That's a great point, and something I think a lot of people don't even really think about if they're not looking at it from a research perspective. And where does this study stand currently, and what have you been able to find so far?
Yeah, so Emily's actually working on probably the second main aim of that project right now. And the first one's fairly well wrapped up. So what we've been able to find so far is that, in fact, there are activity patterns that are altered, not exactly in the way we predicted, of course. I don't find my hypotheses are ever completely right. At least they haven't been yet. Usually some parts different. But we got a little bit close on this one, in the sense that it doesn't seem to be that activity patterns within a single part of your brain are terribly disrupted. If you look early, when pathology is just starting to accumulate, again, that's a big focus of what we do in my lab. But the communication between brain regions is disrupted. And what we think that could mean is that some of the first kinds of memories you might start having problems with are things like involving binding elements of a memory together. So you might remember where something happened, but not remember what happened there. So connecting those pieces together would, in theory, require different parts of your brain communicating, possibly during sleep. And so we've been looking now at reversing that process, and that's where we are right now. And we did that in a way where there's a part of your brain called the hippocampus that seems to be important for linking those different parts of other parts of your brain, if you will, to form these memories. And we've been looking to see if clearing pathology just there using a kind of sophisticated targeted approach was sufficient to reduce a lot of those disease symptoms. And the interesting take-home message from that study so far, we're doing some more experiments to make some reviewers happy right now, so this could change a little bit, but it seems like a lot of the take-home message is going to be you can go in and you can remove pathology fairly early in disease before you've gotten things called plaques or tangles, so kind of the hallmarks, if you will, of Alzheimer's disease. But once some of the tau and amyloid has started to accumulate a little bit, you can go in and clear out that pathology. And we made our models almost completely better. And so at first we thought it completely worked. And so we looked carefully at all the parts of our data, and we realized that one piece had changed. Instead of those two parts of your brain communicating, the brain, if you will, found a different way to solve the task. So the cognitive impairment went away, but it went away because the brain had changed what it was doing, and removing that pathology allowed it to compensate and do the task right, even though it wasn't doing the way it would if pathology had never happened. So what does that mean? One of the neurologists we work with likes to use this analogy that if you shoot a shotgun to the brain and you pull out all the pellets, of course the brain isn't better, right? And so that probably happens to some extent for Alzheimer's disease. There's probably changes that aren't fully reversible, even if you go in and remove some of that pathology.
It's fascinating the way you said it found a workaround essentially for that. Very interesting, and we're so interested to see where things go in the next couple years of your research. You both recently attended the Society for Neuroscience's annual meeting, Neuroscience 2024. Can you tell us about the research that you presented there? Yeah,
so I got to do the press conference for that one, even though it was Emily's data, so I'm going to let her start with this one.
So this gets a little bit more into the sleep of everything. So Aaron mentioned something about a clearance system. So in your body, everything gets cleared through the lymphatic system. If you've heard of the lymph nodes, that's part of that system. Your brain doesn't have a conventional lymphatic system. Instead, it's thought that instead of the brain cells, which we call neurons, the non-neuron cells, the glia, are working together with the lymphatic system to clear out extracellular pathology. So I know that's a lot of big words, but again, pathology is just these proteins that build up. So if you imagine maybe cells like little houses, there's a bit of space between all of them in the neighborhood. And if you live in a neighborhood, your trash man probably comes by once a week to take the trash out. When he takes the trash out, he takes it from the actual trash can on the curb. He doesn't go into your house. So the brain is kind of doing this too. There's a molecule that Aaron mentioned called beta amyloid, and it's just a molecule that hangs out in our system for whatever reason. We honestly don't know what it does truly in everyone, but everyone has it. We have it in our brains right now. But when it builds up, it can form something sticky called plaques, and that can get in the way of communication between cells. And those beta amyloid plaques are one of the biggest hallmarks of Alzheimer's. So my study that I presented on at SFN, Society for Neuroscience, focused on how we could target clearing these plaques from that extracellular space, from that space between the houses, kind of be the trash man on our own, by using sleep. So that glymphatic system, using the glia and the lymphatic system together, it's a very new, about only 10-year-old idea. This glymphatic system is thought to be very prominent, most efficient during slow wave sleep. So in humans, that's deep sleep. In rodents, it's a little different. So my project has been focusing on seeing if we can monitor changes in sleep deficits to see if we can find biomarkers for Alzheimer's early on, before their brains even express this pathology. And then the next leg of it, which we've just gotten into, is very preliminary, lots of pilot and troubleshooting studies going on. But we are actually trying to facilitate this clearance, since this pathology is related to the behavior and the cognitive decline we see in Alzheimer's. We're trying to actually facilitate clearance by delivering a sleep facilitating drug. So trying to amp up that slow wave sleep, trying to amp up that clearance, and see if maybe we can get rid of the pathology, and then we can also somehow heal the brain and the behavior.
That is remarkable. Aaron, did you have anything that you wanted to add to that?
Yeah, no, just that this is a new drug. In fact, we haven't had good sleep drugs that were recommended for elderly individuals because all of our sleep drugs until this one increased the likelihood you could fall. And obviously, if you're older, falling is the last thing you want to do. And so we're excited about this newer drug that can do that, but it also means because it's newer, it needs to be tested. And we want to make sure before we use it in clinical trials in humans that it's doing all the things we want it to do. But there's a lot of evidence suggesting the pieces might fit together, but people haven't really put all of the pieces together yet. And so we're trying to both do that, and we're trying to do it in a new way, kind of fitting with one of our lab themes that Emily touched on, and trying to find the earliest sleep changes so we can catch the disease early and get that pathology clearing out at a point where we can prevent maybe accumulation to ideally prevent the disease from ever developing, but at least slow down the progression as much as possible if we can't do that. So we're excited about where that's going to go and if that will work, and we'll see what happens.
Such exciting research, and I'm never going to forget the way you described the trash pickup and the houses. That's really going to stick with me. So we end every podcast with our bowl of mystery questions. So if you'd like to draw one question and you guys can both answer.
Sorry in advance. What was your favorite childhood movie?
Oh, gosh. Maybe E.T.? That's going to take me a little bit, though.
Oh, good one.
No one's going to know what that is.
Everyone knows
E.T. Yeah, of course. Emily?
That's a tough one. I think me and my brothers really like The Sandlot.
That is a great choice.
We had a Mastiff, so we would watch it with her, of course.
You're like, the dog is here in real life.
Exactly.
I love that answer. Well, Aaron and Emily, thank you so much for joining me today on Nole Edge. And if you would like to learn more about the Wilber Lab at FSU, visit wilber.neuro.fsu.edu, which we've linked for you in the description box. Thanks for tuning into Nole Edge, and we'll catch you next time.